finding equations of tangent lines over and over. You remember doing this? We did this so many times. And so I just want to let you know that as we work on a couple of these questions are just going to be total review with a little bit of new stuff at the end. All right, so let's fill in the blank. It says the tangent line can be a good approximation for values close to the point of tangency. Yeah, point of tangency is what we're talking about. And so while I'm writing this, maybe you're writing it too, let me ask you the question. I've asked you this 1,000 times. I'll keep asking it as needed. If you're going to find the equation of a tangent line, you've got to have two things. What are they? Point of tangency and slope of the tangent line. I encourage you to say, you're right. I encourage you, though, to say more than just point and slope, because if you use those other keywords, I feel like it directs you on what to do. So if you say slope, that carries one meaning. And honestly, my Algebra 1 students, they know what slope is. They do, and they can find slope really well, just like you probably. But if you were to say slope of the tangent line, they'd be like, what kind of line? You guys actually know what that means. And so slope of the tangent line pushes you in a specific direction versus just slope, right? So we want the point of tangency and the slope of the tangent line. So when you look at question A, for number 1 there, number 1 gives us that function f of x equals root x. And it says find the equation of the tangent line at the point 2 comma root 2. Of those two things you need, which one did they just give you? Yeah, the point of tangency has been given to you. We, however, need to find the slope of the tangent line and put it together to find the equation of the tangent line. All right, so this is something we've done many, many times. Doesn't mean you're perfect at it. It might be a little rusty because it's been a little while. Let's see if you can do part A. Okay, let's find the equation of the tangent line, and then we'll use that with a couple of these other questions. You will need your calculators on some of this, so please, if you don't already have those out, go ahead and get those out. We'll use those in just a minute. Let's see what we have here as far as finding the slope of the tangent line. In order to find the slope of the tangent line, we need to understand what that language is really talking about. So slope of the tangent line needs to be interpreted as what? The derivative, and specifically which derivative?
First.
Say again? So I said her first derivative, yes, but slope of the tangent line carries a very specific meaning. Think about Leibniz's notation. It's not dr/dt what we're talking about, right?
dx dy.
dy dx. Yeah, we're talking about dy dx. So, yeah, the derivative is correct. First derivative is correct. But if you wanted to be really specific, you would say dy dx. So, dy dx, I'm just going to write that as f prime. Of course, they essentially mean the same thing. So, f prime of x, let's check our derivative. It would be 1/2 x to the negative 1/2, right? 1/2 x to the negative 1/2. I really think you could accomplish part A without a calculator. Part B, not so much, but part A, definitely. Of course, that's the slope of the curve at any point. We are not interested in just that. We are interested in the slope of the curve at our point of tangency, right? So I need to plug a number in to get our slope of the tangent line. What number do I plug in? 2. Okay, so if I plug in a 2, I get f prime of 2 is equal to 1/2 times 2 to the negative 1/2. And so overall, if I finish this up, it would just be 1 over 2 root 2. You guys agree with that? Okay, so 1 over 2 root 2, that's the slope of the tangent line. So to get the equation of the tangent line, I just got to take it that one step further, and I would write it, I usually use point slope, as I mentioned before. Y minus root 2 is equal to 1 over 2 root 2 times x minus 2. And I would just leave it right there. You can, of course, put that into the slope-intercept form if you want to. That's not a problem, but you can leave it like that, and that is definitely an equation of the tangent line. Okay, question? Yeah?
For the loop list tomorrow, can you use my calculator?
I think it's no calculator. Oh, somebody asked me that and I forgot to check. Remind me before we go and I'll look it up. Yeah. Okay, so any questions on that part right there? We're good? Okay, so then moving forward, let's take a look at part B. And I'll kind of see it right there. Part B says, approximate f of 1.8 using the equation of the tangent line. I would like to show you again what we're really doing here. So let me draw a graph of our function, and you can check this on your calculator if you want, but the graph of the original curvy function should look like this. Oops, let's try that again. Right, root x, y equals root x, does that ring true to you guys? Okay, so y equals root x is the curvy graph what did we just find in part A? It's not a curvy graph. It's a line, right? And so if I were to graph that line, it would look something like this. Here's 1, here is 2. So, there's my point of tangency right there. So I will do my best to get this. Yeah, that's not too bad. So we found the equation of that blue line, didn't we? That makes sense? And so close to the point of tangency, like we said there at the very beginning, close to the point of tangency, the blue line is really a pretty good representation of the curve, right? But the further you get from that point of tangency, the blue line becomes a worse approximation for the curve, right? So if you look at what we're going to do in part B, it says approximate f of 1.8. I chose 1.8. Why? It's pretty close to 2, right? Now, of course, your definition of close could be questioned there, right? But it's pretty close to 2. I think we could all agree that it's at least sort of close to 2. So this says use the equation of the tangent line. Not use the curve, but use the equation of the tangent line to approximate f of 1.8. So in other words, use the value of the tangent line to represent the value of the curve. Make sense? Yes? So we're working on approximation. This is a skill that is often not emphasized in any math class, usually, right? Usually the skill is find the answer. And hopefully it's right, right? So here we're asked to find the approximate value of something. That's a little bit outside of our normal questioning, right? And so let's go ahead and try this together here, f of 1.8. So what they're asking us to do is they're saying use the tangent line that you just found. So I need to take that 1.8 and I need to plug it in for something, right? Am I going to take that 1.8 and I'm going to make it the input of the curve? Am I going to make it the input of the line? Or maybe something else? What do you think? 1.8. Obviously it's an input, right? It's x. So is 1.8 going to go in for x in the line, in the curve, or something else? The line. And then, if you want to be really bold about it, don't they tell us to use the equation of the tangent line? They tell us, use the line. I ask the question because I see people get confused, right? They're like, oh man, do I plug 1.8 into this or that? They asked you to use the line, so let's use the line. So here's what it might look like. You could write something along the lines of y minus root 2 equals 1 over 2 root 2, and then in place of x, you just write 1.8. So 1.8 minus 2 in there. Here's where the calculator would probably be, we could probably handle this without a calculator. We really could. But maybe we just use the calculator here to finish this off and get a decimal answer. And then we'll work with that here again in just a second. So go ahead and get the y by itself, add root 2 to both sides. Let's get a decimal answer. You could do it without, but let's just use it here just for a little bit of practice with that. For right now? Oh, yeah, I think so. So once you guys have that approximation there, or that value, let us know and we'll compare what you got. Any volunteers for an answer? Yeah, Mandy, what'd you get? 1.344. We in agreement on that number? Okay. So 1.344. Then I'm going to put this symbol right here is approximately equal to f of 1.8. So when the input is 1.8, the output of the line is 1.344, right? And we are approximately equating that to f of 1.8. We're saying the curve is approximately that. Not exactly that, of course, but approximately that because the tangent line is a good approximator of a curve at least close to the point of tangency. We've done that as well. Do you guys remember doing that? Maybe a little bit? Yeah? Okay. So the final thing we're going to do is part C. And part C says, is the approximation from part B, is it too high or too low, and why? So we're going to approach this from a couple different angles. We'll narrow it down to what we need to do. So look back at the graph that I drew for you in part A. Based on that picture of the graphs there, would you say that our approximation using the line is too high or too low? Can't you see how the line is, with the exception of 1 point, isn't it always above the curve? Every single time, with the exception of the point of tangency, it's always above the curve. So, yeah, I agree. Our approximation is too high. let's just be honest. Like if you said, I think the approximation is too high, that's correct. But if your reasoning was, I looked at a graph and I think I could see it. Graphs will sometimes lie to you, won't they? Especially if I drew it by hand or you drew it by hand. Who's to say that line is the exact right angle? And this is a relatively simplistic example, but others could get a lot more complicated, couldn't they? Just how does this curve behave with the line? And so saying, hey, I looked at the graph, and listen, I would question our ability to quickly and easily graph something and accurately graph something in the midst of a quiz. I mean, seriously, can you imagine that? What if the question demanded you to precisely and accurately graph this curvy graph, and then precisely graph this line at exactly the right angle, and then look at it and be like, yep, too low. That's asking a bit much of you, isn't it? Especially if you don't have the calculator. Even if you did have the calculator, there's only so many pixels, right? The pixels sometimes kind of join up, and you're like, have you ever looked for an x-intercept and the curve goes right up to it, and you got to zoom in like 4 times to even see, okay, does it touch, does it not touch, does it cross twice, And so graphs are inherently a little unreliable as far as our powers of observation, so there's a better way, okay? So what we're going to do with C is actually find that better way, and I think compared to trying to graph something by hand, you'll find this to be much easier, much easier. So let me get to a better spot on my screen here, and we'll try C. Or is it too low? Did you guys notice on that graph? Maybe I'll reproduce that graph really quick here. You all saw it before, but I'll just draw it over here. Here is the curve. Oops, here's the curve right here. Here's the tangent line. How would you describe the curve? Like, what are some words you could use to describe it? It's concave down, yeah. I'd say increasing as well, right? This looks like it's going to be increasing the whole time, but concave down is a very key feature. That's the feature we're going to actually use here. So what function describes concavity? Double prime, f double prime, g double prime, whatever it happens to be. And so what we're going to use is we're going to use f double prime to help us come up with our reasoning. So let's go ahead and find f double prime. Of course, that's based on what we had earlier for f prime. So let's see if I can remember this. F double prime, what would it be? It'd be negative 1/4, right? X to the what? Should be negative 3/2, right? So 1/4 x to the negative 3/2. So if we are trying to determine concavity, like concave up or concave down, then we are really looking for where f double prime is or positive, right? Looking at the sign of f double prime, positive or negative, will tell us the concavity of f. So if I'm trying to figure out where f double prime is positive or negative, what would be a useful number for me to consider? 0, right? Because wherever f double prime is 0, that'll probably tell me some hints about where f double prime is positive or negative, right? Okay, so let's go ahead and say f double prime equals 0. I have this wonderful little equation. Let's try to solve it. What would you do first to try to solve something like that? Yeah, multiply by negative 4, divide by negative 1/4. Same thing, right? So essentially, aren't we getting rid of the negative 1/4? Because anything times 0 is 0. So I think we could write x to the negative 3/2 is equal to 0. Let's keep going. What else could I do? Trying to get the x by itself, right?
Could you do the cube root?
Well, before we do that, I think the negative exponent, sometimes we shy away from dealing with the negative exponent. I think we need to deal with the negative exponent. What does that really mean? Yeah, flip it down. Yeah, so it'd be, like you said, Mandy, 1 over x to the 3/2. And here we arrive at, I think, kind of an interesting point. That takes on a little bit of a different look, doesn't it? What part of a fraction has the power to make the whole fraction 0? The what? The numerator, right? The numerator is the only part, right? Think about it. If the denominator is 0, what's the value of the fraction? Undefined, does not exist. If the numerator is 0, the value of the fraction would be, assuming the denominator is not also 0, right? Yeah. And so you look at this and you say, all right, what's the numerator? That's not going to change, is it? So is there any way this fraction equals 0? There is no way. So this will never equal 0. And so knowing that this is a continuous function and the fact that f double prime will never equal 0 doesn't that mean that f double prime will always be positive or always be negative? We just got to figure out which it is. So maybe do a quick test value. What test value might you use?
The second derivative.
Yeah, use f double prime, but what test value? Like what number would you plug into f double prime? 1. I like it. So f double prime of 1, what's a nice easy number, right? Equals negative 1/4 times 1 to the negative 3/2. Well, what's 1 to the negative 3/2? And times negative 1/4 is negative 1/4. What's the most important part about that number? It is negative. So I'm just going to put is less than 0. So we can say then that f double prime is negative on the interval 0 to infinity. Therefore, f is concave down on that same interval. Finally, we can reach our conclusion. Therefore, the approximation is to what? High. That's right. So if a function is concave down around that point of tangency, the approximation will always be too high. Yes, ma'am?
So I'm just kind of confused on how we got like from the equations undefined to like plugging in 1.
Yeah, good question. So we didn't say the equation was undefined necessarily. We just said that there's no way that the f double prime would equal 0. And so here was the reasoning I used. I'll say it again. I hope this works. Let me know if it doesn't. If f double prime is continuous on its domain, which it is, and it never equals 0, then doesn't f double prime have to always be positive or always be negative? It's got to be one of the two, because if a function, I'm using the IVT here, if a function is continuous yet never equals 0, it has to always be above the x-axis or always be below. So I said, okay, fine. So if it's always above or always below, then I just need to do a single test value, and that should tell me the sign of f double prime on the entire domain.
Okay, so just like pick a value on the domain.
Yep. You know, realistically, hopefully a perfect square, one of which is 1, right? And then we can use that to determine the sign of the entire interval for f double prime. Yeah. Question?
If f double prime could equal 0, what would you do then?
That's example 2.
Oh, okay.
We'll deal with that next. Madison.
I'm confused where this 0, 8 and I'm looking for.
Oh, my infinity kind of got twisted there.
Oh,
I don't know what I was thinking, or if my infinity got twisted. Yes, that's 0 to infinity. You know how sometimes you guys misspell t by writing x?
yeah.
I misspelled infinity, I'm sorry. I don't know what to tell you. Sorry for the confusion. Okay. Any other questions? So whenever you're justifying whether the approximation of a tangent line is too high or too low, we're always going to use the second derivative leading to concavity, then we do our conclusion. Make sense? Okay, so let's address Caroline's question from a second ago. Wasn't the concavity consistent? The concavity never changed. It was, the function was concave down for the entire graph. Example 2, not so lucky. What does the graph of sine look like? Isn't it like constantly changing from concave up to concave down over and over and over? So we're going to have to target some specific values. That's kind of the short answer to your question, Caroline. You're going to have to be a little more specific instead of just saying, hey, it's always concave down. We're going to have to be specific to what we're talking about with the interval. So, all right, so part A hopefully looks even more familiar now. Part A says find the equation of the tangent line. Just a reminder, to find the equation of the tangent line, you must have the point of tangency as well as the slope of the tangent line. And, you know, Christmas is coming up. I've gifted you with the point of tangency. Merry Christmas. The only thing you got to really work for is the slope of the tangent line. I say that because I was at Home Depot this weekend, and what was the front of the store? Christmas. Christmas. Yeah.
Already putting up Christmas tree.
Craziness. Yeah, I'm like looking at Santas and Christmas trees, and I'm like, it's October 30th or whatever, and it's 81 degrees. This doesn't feel right. Like in the mall, like in the main part of the mall.
Like right in front of Dillard's.
Wow, that's crazy. Just doesn't seem right. Caroline, what's it? Let's hear your derivative like before. We're looking for the derivative dy dx. Maddie, what'd you get for g prime for this one?
2 cosine of 2x.
Nicely done. So Maddie used a rule. Maddie used a rule to get g prime. What rule did she use? Chain, yes. That's where that extra 2 came from. So g prime of x equals 2 cosine of 2x. And I think we can do a without a calculator. Hopefully you were able to do that, or at least consider it. That, of course, is the slope of the tangent line at any point on the curve. We want to know the slope of the tangent line at our point of tangency. So what do I need to plug in to get our tangent line slope? 5 pi over 8. So it's going to be g prime of 5 pi over 8. Guys, just, hey, listen, many of you have this down pretty solidly. Others, the notation is a little confused. If I were to write this, I'm about to erase something. Are you all watching? If I were to write this, but in place of that, if I were to put this, do you realize that that's technically totally incorrect? Right? G prime of x is definitely not that number to the right. It's not even close. I mean, technically you are in the wrong category totally. So, I will often, be kind and not take any points off for that. But I just want you to know that it really should be g prime of 5 pi over 8, because g prime of x is the equation we wrote above. Plugging in a 5 pi over 8 means we're finding a specific value. It's not g prime of x anymore, it's g prime of 5 pi over 8. So I just want to let you know that that's a pretty important communication thing as far as telling the reader what it is you're trying to find. Unit circle, right? The 2 and the 8 cancel to be 5 pi over 4. What is cosine of 5 pi over 4?
Negative 1 over root 2. Or
Right.
root 2 over 2.
Yeah, negative root 2 over 2. Yeah, so then wouldn't the 2's cancel out? So you'd end up with negative root 2. Again, in our continuing quest to master the unit circle, I would hope that that is something that you would be able to do without a calculator. All right, so then our final step in part A would be to write the equation of the tangent line. So that would be y, I guess it would be plus, wouldn't it? Y plus root 2 over 2 is equal to negative root 2 times x minus 5 pi over 8. And that's the equation of the tangent line. Should be able to do that without a calculator and hopefully do well. So there's that. Any questions on that part? Now let's see if you can do B now. B, definitely want a calculator active. So B says, using the equation of the tangent line, approximate g of 2.1. So this is, of course, you can see very similar to what we did in part B on the previous question. Take a moment and try part B. Let's find that approximation of the curve using the line. And then we'll try to tackle part C. Mm-hmm. Mm-hmm. Okay, Ashley, can you explain what you did for part B?
So I just plugged in 2.1 for the x in the equation of tangent line.
Okay. So that initial plug-in, of course, would look something like this. You described it very well. Okay, and so then you do the arithmetic, right? You add some stuff or subtract some stuff from both sides. Ashley, what'd you get for a number?
Negative 0.9 LFO.
Yeah, that sounds about right. You guys get the same thing? Others? Yes? Okay. So, isn't that the output of the line when x is 2.1? And so then to connect it with the question, I think, like before, we would want to say is approximately equal to g of 2.1. Like I said, connecting it with the question that they asked. It's not enough just to say, hey, I found an output of the line. Say, okay, and that's actually the approximation for the curve. Mandy.
So is that worth the point then, saying that it's approximately equal to G?
It really would have to be, right? Because otherwise it's like, did you really actually address the question,
Yeah.
right? Because ultimately they said approximate G of 2.1. So somewhere in there you got to say, and this thing is approximately G of 2.1. You really do. Otherwise you didn't really address the question. Yeah. Okay. Any other questions? That's a good one. Okay, so then oh yes ma'am, go ahead.
Do you have to put the y equals there, or can you just do the g?
I think you'd be okay without that, right? Because, we can see from the previous step that you used the line.
Okay.
And clearly you added some stuff and multiplied a few things together, got a number, and then the important thing is to say, and that's approximately equal to G of 2.1. Yeah. Okay. So let's tackle the other part here, part C. Part C, just like like a number 1 says, is the approximation for part B too high or too low? As before, we are going to use the second derivative connected with concavity to help us get there. So, first thing we ought to do probably is find G double prime. Let's find G double prime. So take a minute to do that, and we'll check your answer here in just a second. Okay, Riker, what did you get for G double prime?
-4 sine of 2x.
So Riker said negative, hang on just a second. G double prime of x equals -4, you said sine of 2x. Where did the 4 come from? Got to do the chain rule again, right. And so that 2 that used to be there gets multiplied by 2 again, doesn't it? Yeah. Okay. So you guys all okay with that second derivative? G double prime -4 sine 2x. Okay. So we are interested in where G is concave up or concave down. So then more specifically, we're interested in where G double prime is, because we want to determine positive or negative, right? So let's go ahead and set G double prime equal to 0. And this is where your old friend, the unit circle, gets to make another appearance. I keep calling it your friend. I figure if I say it enough times, you'll be like, I think that's my friend. Okay, so if we're going to solve this, what would be your first step? Sure, divide by -4. I think is a good step. So sine of 2x is equal to 0 after you do that division. And then what about that next step? This is the step that people often sort of brush right on by, but it's pretty important. What do? Inverse sine of both sides, right? So it's just a regular old equation solving method. Inverse sine of the left side, inverse sine of the right side. There we go. So the inverse sine and the sine just cancel each other out. That's why it's called inverse sine, right? They cancel each other out. So 2x then equals the inverse sine of 0. It's a pretty easy unit circle question, right? Inverse sine of 0. In other words, where is sine 0? At what angle is sine 0? Or what is the y value? Where is the y value 0? Right, that'd be another way to say it. So what do you think? Yeah.
It's all the 0, pi, 2 pi.
Yeah, 0 plus or minus n pi.
Yeah.
Yeah. So I'll just write out a couple of those. 0, pi, 2 pi, 3 pi, so on and so forth, right? Dot, dot, dot. So to finish this out, we need to divide by 2, right? So then for our final candidates here, we get x equals 0, pi over 2, pi, 3 pi over 2. Hopefully we did enough. Dot, dot, dot. So these would be all the places where G double prime is 0. Correct? So in between those, in between any of these values, G double prime should either be positive or negative. Make sense? And so, we basically created a bunch of intervals here, from 0 to pi over 2, then from pi over 2 to pi, and then from pi to 3 pi over 2, so on and so forth. What we need to do is we need to pick out the interval that works and makes sense for us. Here's how we determine that. What was the x value for the point of tangency? 5 pi over 8. I'll just write that up here because I've got space. You can write it wherever you want. And then what was the x value that we used to approximate with? 2.1. Now if I wrote a good question, both of those numbers should fall within the same interval of those intervals we just made. Make sense? both of the numbers, right? So if 5 pi over 8 falls in one interval and 2.1 falls in another interval, I've written a question that you really can't answer. I've written a bad question, okay? So both of those numbers should occur between two of those values in the intervals we created. So, in other words, 5 pi over 8 and 2.1, do they both fit between 0 and pi over 2? No, because isn't 5 pi over 8 bigger than pi over 2? Okay, so then do they both fit between pi over 2 and pi? You can do this without a calculator. Pi is 3.14159, right? Isn't that bigger than both of these? Okay, pi over 2 is approximately 1.57, right? Half of pi. So do you see how both of these actually do fit into that second interval? Okay, so if you wanted to, you could graphically represent this with a sign chart for G double prime. So you could say G double prime, and you could have, 0, pi over 2, pi, so on and so forth, like that. But what's the only interval we really care about? Pi over 2 to pi. Yeah, we only care really about this interval right here, because that's the interval that actually contains the point of tangency as well as what we use to approximate. So, we just need to test that interval out and determine whether G double prime is positive or negative within that interval. The calculator's active here. What would be a good test value in your mind for us to use? Sorry? 2 or? Would 3 work? Isn't 3 a little bit less than pi? So I'd say 2 or 3 would be the most logical. Now you could use some pi expression, like you could use 3 pi over 4, 7 pi over 8. I mean, since you got the calculator active for this part, there'd be a wide variety of things you could use. But you could just use literally 2 or 3 also. So let's do a test value and see how this interval works out. And we'll conclude. Macy, what test value did you use?
I used 2.
Okay, so when you figured out G double prime of 2, what did you get?
3.027.
What's the most important thing about that number? Yep, that makes sense? Okay, so what that has essentially established that on that green interval right there that I've marked, G double prime is positive. So here's how we can conclude. We'd say something like this. G double prime is positive on the interval pi over 2 to pi. And of course that interval contains our numbers, right? Therefore, since G double prime is positive on that interval, that means G is what? Concave up, correct. Concave up on that same interval. Therefore, we can say the approximation is 2. Low, yeah. So concave up means any approximate tangent lines, any tangent line approximations will be too low, for the exact opposite reason of what we saw in example 1. What do you think? Do you see how that's more precise than I looked at the graph and I saw something? Right? It's actually, we're locking this down using precise numbers and language. Okay, so I'm going to show you one last thing here. This last thing is more of a foreshadowing of Chapter 4. And so really what we just did concludes the quiz material. What follows is something that if on the off chance that we just have loads of extra time, it's interesting. But the main part here is that it foreshadows a little bit of Chapter 4. So this will just take a second. Anybody remember who came up with this notation right here? German guy. Name starts with an L. Leonardo da Vinci. That sounds good. That sounds really good. It's Leibniz. So that's Leibniz's notation for the derivative, right? Who came up with the other one? Yeah, Newton, the English guy, right? So there's a German guy and an English guy. Newton came up with that one. So one of the handy things about dy dx is it literally is just a fraction. And so you could, like manipulate it like a fraction. So what if we took these instructions here and did them? Multiply both sides of that equation by dx. What would we get? Yeah, dy equals f prime of x dx. And so we would call the dy a differential. We would call the dx a differential. And so dy is simply the differential of y, dx is the differential of x. And if you see the word difference in differential, you're seeing it correctly, right? It's just a small change in x or small change in y. Here's the point. Here's the foreshadowing. Please don't start packing up now. I got 1 minute. In chapter 4, we're going to be looking at something called the antiderivative, which, as you might guess, is the exact opposite inverse operation of a derivative, right? It's also known as the indefinite integral, is the word that's commonly used. So this symbol right here stands for the indefinite integral, or the antiderivative. So if I were to anti-differentiate both sides, we're going to learn that the antiderivative undoes the differential. They just cancel each other out, more or less. And so the antiderivative of dy is just y. What would you guess the antiderivative of f prime would be? It would just be f. And then the final thing I would mention here, because a lot of folks, I think, rightly ask this, they ask, where does the dx go? Let me just remind you that when you started doing derivatives, you were always doing the chain rule, right? And wasn't the chain rule the unpackaging of the boxes? So wouldn't the antiderivative have to be the repackaging of the boxes? So what happens to the dx? Honestly, it just gets integrated back into the input. The little box just gets repacked inside. And that's where it goes. So, and we actually also put this little mysterious plus C thing on the end. Mysterious and interesting enough, I made a whole shirt for it. That's what the plus C thing is in the back there. So we'll explore that in chapter 4. But that's just a little foreshadowing, so don't get too concerned about that last little bit. So, see you for your Luke quiz tomorrow.